Welcome to the third weekly robotics meetup, and we'll kick off now with the presentation from Ignat and Adrian about their Formula student experiences. So I don't know how you want to do this, but the floor is yours.
Thank you. Adrian, should I just share my screen for the presentation? Cool. So, hi everybody. My name is Ignat, and I'm here today to talk to you about the wonderful world with Formula Stone Driverless, along with Adrian. So yeah, first off, let's kick it off with what actually is Formula Student. It is by far the world's biggest educational competition. In a nutshell, it challenges students to design and build a race car similar to the ones you see on the screen, and do that from scratch as much as possible, design and build as much as possible from it. Obviously, the whole aim of the competition is to develop the next generation of talent, because everybody involved is a student after all. And the competition itself is quite massive. I think now, or at least back when it was running in 2019, it was spanning across 5 different continents, 13 different competitions, and each year it managed to bring together more than 50,000 students. But this is a robotics meetup after all, and we're more interested into the new developments of Formula Student, or the so-called Formula Student Driverless competition. It was introduced in Germany, or Formula Student Germany, back in 2017. And the whole idea was to challenge students to make these self-driving cars. And the competition has kind of split into 2 separate branches over the years. There's the Formula Student Germany branch, which challenges students to take one of their existing cars from previous years, equip it with all of the sensors for autonomy, computing for autonomy, and develop the software to make it race as fast as possible. And then there's also the branch of the UK competition, where instead of students having to build their own cars, the competition organizers supplied them with cars like the one you see here in the image above, and students helped only put on the sensor suite, computing, and develop the software. For the purposes of this presentation, for the purposes of this presentation and simplicity, we're just going to focus on Formula Student Germany, where students are building their own cars altogether. Obviously, Formula Student Driverless is responding to the movement around autonomous vehicles in the recent decade, and it aims to encourage interest in students with this novel technology, and I would say in general robotics. I can say that it certainly worked for me. I find autonomous race cars like these way more exciting than the Lego robots I have to build from university classes. And yeah, who are we? My name is Ignat, and I'm the founder of Edinburgh University Formula Student, or EUFS for short. I have now since graduated, that is last summer, and working for an autonomous driving startup called Copernicus Automotive. And my colleague who will be co-presenting here is Adrian, who is a member from AMZ, which is the ETH Zurich Formula Student team. He has now moved on to do his master's thesis in the Autonomous System Lab, again at ETH Zurich. And this is the point where things get a bit weird. As you can see, me and Adrian are from 2 different teams competing in 2 different competitions. I have competed in the UK competition and he in the Germany one. So this presentation is going to be not really about what our teams individually do, but more about sharing what Formula Student Driverless is and what it can teach people, and obviously about the exciting technology behind it. So the rest of the presentation is just going to be a mismatch between my team and his team, where things get interesting. Yep. And a bit about the competition structure itself. The Formula Student Driverless competition is split into 2 categories of events. The first one being static events, which are mostly presentation-based and a bit boring. There's 3 of them. The first one is engineering design, where we students are asked engineering questions based on our design decisions and how we have made the car, effectively to assess how rational and how efficient we've been in designing all of this. Then there's cost and manufacturing, which assesses how expensive is the car and how manufacturable it is. And finally, the business plan sees us role play a startup to try to turn this car stuff into a full-fledged business. Then we have arguably the more exciting part of the competition, which are the dynamic events. The dynamic events are obviously where we actually see the cars on the racetracks and see them go fast. Because the Formula Student tracks really are very narrow and unlike F1 tracks, for example, the boundaries of the Formula Student tracks are actually signaled with these high contrast yellow and blue cones. We use blue on the left-hand side and yellow on the right-hand side, which also aids with the perception problem that the autonomous cars face. The dynamics events are 4. There's acceleration, which is what you see here in the picture on the bottom right. The car just has to drive 75 meters straight and stop at the end, hopefully without crashing. Then we have skid pads, which is an event testing the agility of the cars, where the cars have to drive in a figure of 8 in like really low radiuses. Then we have autocross, which is where things start to get exciting. Autocross is where the car has to drive a single lap as fast as possible around any unknown race course. So the layout is completely unknown to the car beforehand, and the car must actually learn the layout and drive around as much as possible. And then we also have track drive, which is 10 laps around that same unknown race course. And actually, for the purposes of this presentation, we're going to focus only on the track drive event. And just to tell you a bit more about it, it's 10 laps around an unknown race course, so we have no prior data about how the race course looks. We have to figure that out online. Each lap is around 200 to 500 meters long, and the team with the fastest total time around all of those 10 laps wins. And yeah, I think that's everything from me. Now I'm going to hand it off to Adrian to start speaking about the hardware of the autonomous cars.
Cool. Thank you, Ignat. So typically, the autonomous car has starts from the base, which is a car developed from a previous year. So these cars are usually electric, but could be fully combustion-based. But we're going to focus on what we're familiar with, which is these four-wheel drive electric cars. So assuming that you have an individual motor controlling each wheel, you can do nice things like torque vectoring. And with the regenerative braking of the car, you can have full drive-by-wire capability. So strong acceleration, strong braking, all by controlled by a low-level controller. The cars typically have a top speed of around 115 kilometers an hour based on that 75-meter acceleration event. So that's about 32 meters per second. But in these curvy track drive events, you likely won't ever reach that speed. The rules designate that you have to have a maximum of 80 kilowatts at any given time, and they have sensors that track the amount of power going out of the battery. So this is kind of the upper limit on how much power you can put out to the motors. And then, at least taking an example of the AMZ car from my year, it's about a car with all sensors attached and fully autonomous is about 200 kilograms. Next. So for the steering, it's pretty simple. A typical steering setup is to control the driver steering column, and typically with a belt-driven motor and a stock motor controller from a manufacturer that would accept position set points from an encoder. So nothing too crazy there. And then the modeling of this will be propagated down the chain to whatever controller that you have for your system. Next. Oh. In terms of the sensors, typically in our fantasy car, we have a limited budget. So we have 2 Hesai spinning LiDARs, one on the front wing and one on the roll hoop. The roll hoop one is to see as far as possible, and the front wing one is to get as many points as possible on the close cones. 3 cameras, 2 in a wide wide-angle monocular setup, but a third stereo camera facing forward to at least get depth on the cones that are right in front of the car. Next. Plus a GNSS dual antenna and an IMU at the car center of gravity. The nice thing about the dual antenna is that it gives heading information in terms of yaw rate and absolute yaw as well, and can do better than a single antenna GNSS for position estimation. And finally, there's a ground speed sensor, which kind of works like an optical mouse, but is a very expensive F1 level component. So typically those are given to the team by a very nice sponsor. And they measure absolute velocities of the car relative to the ground. In terms of compute, a very typical setup would be a very high-powered Intel CPU, because remember, if you got an electric car, you've got you might have as much as 600 volts available to power your compute system. So typically, battery isn't really a concern when compared to the motor batteries. But you'll want typically an industrial motherboard that's vibration and shock resistant, just due to the nature of going fast. And for a GPU, I just picked the one that's coming out of the car that I was working on, which is an NVIDIA GTX 1070 to run the neural networks for perception and others. The Jetson systems are definitely an option, but it depends on what kind of controllers you're running, because many of the optimization-based controllers are going to have very high requirements on the clock rate of your CPU. And Jetson is just completely limited to around 2 gigahertz, which won't work for some of the fancier control algorithms. Next. In terms of the concept of how the car is designed to work, or the state machine, there isn't really any decisions to be made. So it's a pretty simple start. Just click the start button. Typically, the first lap will be some sort of mapping lap where you're trying to use as robust as possible a system to find the layout of the track, and then doing the final 9 laps with the map fixed and with a fancier controller that can take advantage of the full dynamics of the car. In terms of the see, think, act cycle, that's pretty typical for autonomous robots. Perception is going to filter all the images, the raw sensor data, and give out cone positions relative to the car, which will be mapped by a mapping and localization system, which will then output the cone positions and the car pose in the world frame to the control algorithm. Next. Let's talk a bit about it. We'll give a quick overview of the perception. For camera-based cone detection, typically you'll have some... YOLO V3 is a very popular choice for giving the bounding boxes. And one nice thing about Formula Soon is that there's actually a pretty strong community, at least in terms of sharing open source tools and data. So there's this FSOCO dataset, which has a community model based on access for everyone who contributes to the dataset. And if you're a new team, you can just, instead of contributing images, which are hard to acquire until you have a car, you can actually trade access to the images in return for annotating images that already exist but don't have any labels yet. And there's a link in the bottom to take a look at. But you can find the cones with the bounding boxes from YOLO, and then you can triangulate them with the stereo if you have a stereo setup. Next, there's some LiDAR detection. So first, this is another simple pipeline. You accumulate the scans across the 2 LiDARs, then you can remove the ground to get just the points that you're interested in. And then from that, with some filtering and some Euclidean clustering, you can come to the things that look cone-shaped, that are the right height and have enough points for you to be certain that they exist and are cones.
Cool, so I guess it's back to my turn. Yeah, I'm going to be talking a bit more about localization mapping and then planning and control. So a typical localization mapping system would look something like this, where there's 2 major components. One is the fundamental state estimation, or in our case, we call it EKF localization, which takes data from the IMU, GPSs, and wheel odometry, fuses all of that data, and then proceeds to give its current state estimate to a SLAM algorithm, or in this case, FastSLAM, which has the very important job of building the map of the world around the car, which is expressed in cones. And the cones themselves we just received directly from the perception systems that Adrian talked until now. And yes, then after map is built, we use the data. I'm going to talk about that later. Our state estimation system, or the EKF, is nothing fancy. It's your typical common filter approach, where we fuse a lot of input data from various different types of sensors, fuse it together in the measurement update step, and then use a custom process model in the prediction step, along with the controls given to the vehicle to get better predictions, do the update prediction steps, and spit out the current state estimate, which in our case is a 6-state state estimate. Then the SLAM algorithm itself, we chose for this fantasy theme to go with the old school FastLAM V2 algorithm, which is a very scalable approach based on cone landmarks. And the formless problem is nicely situated where we actually have nice landmarks in the forms of cones. The whole idea is that the algorithm runs in full SLAM mode until loop closure has been detected, or until the end of the first lap. And afterwards, for the remainder of the dynamic event, or for the remaining 9 laps, we switch only to localization mode and safe compute that is then provided to other algorithms. Planning and control. So our system has 2 main, versions of this planning and control. First, we have local mode, which is done during the first lap, and then we have global mode, which I'm going to return for afterwards. Local mode is where, remember, we're still building the map of the surrounding racetrack, and we really don't know how the racetrack is going to look like. The map is always changing, cones are not always detected correctly. So because of that reason, we try to be very, very conservative during the first lap and just make sure the car finishes the first lap. So this is expressed here in the slide. We are very conservative with our planning, and we simply plan a path through the middle of the racetrack. And this is done by triangulating the middle of the racetrack with the detected cones from the map. After we have this middle path of the race course, we give the path to a controller, which in this case is very simple and robust. Speed is controlled by simply calculating the maximum speed as a function of path curvature and length, and then just get acceleration commands via simple PID. Lateral controlling, or steering controlling, is a bit more complex. It's this so-called feedback feed-forward controller, which is just a fancy term for saying there's 2 PID controllers accounting for positional and heading errors independently. Now, after we do the first lap, we go into global mode, which is where things get a bit more exciting. Global mode is where we now have the full map of the race course, and we can now optimize a better path than before. So we take the reference middle path for the race course and fit that through Path Optimizer, which aims to find the path of minimum summed curvature, which doesn't exactly translate to minimum lap time, but it's about there. To do that, we use this QP solver to minimize the curvature, and this is done by moving the path points around the normal vectors to the track width. And obviously, this method is constrained to the maximum curvature and lateral acceleration that the car is physically capable of, which then lends itself nicely to constraining the control algorithms. For controlling the car, we do model predictive control trajectory optimization in a receding horizon fashion. The algorithm we chose to use for this fantasy car is this fairly novel MPPI controller, which forward samples multiple possible trajectories and then cost-wise averages them to obtain the probabilistically most optimal one. But we can't really feed trajectories optimized like this to the car directly. Instead of that, we feed the trajectory to a lower level AOPR controller, which stabilizes the car around that optimal trajectory. And with that, we kind of arrive at the system overview diagram, which we can return to later in the Q&A section. I find it like as a nice map to navigate the whole system. But yes, this is more or less the summary of our major systems operating in a Formula Student driverless car. And last but not least, we want to talk about software infrastructure. This is by far the most overlooked but important part of the team. The job of software infrastructure, or the team of people working there, is to facilitate development for the rest of the team or the rest of the systems that we've been talking until now. Part of the responsibilities of these people include vehicle software interface, developing the simulation, CI and tests, state monitoring for when things go bad in the vehicle, and data collection and processing. We're going to be focusing more in particular in the bolded bits, so simulation and data. For the simulation, we actually developed a custom simulation in Gazebo for Formula applications. The aim was to simulate everything apart from high visual fidelity stuff, which Gazebo is natively not very good at. We also have a couple of custom developed plugins for simulating this, namely a vehicle dynamics plugin and a sensor simulation plugin, which is fitted to real-world data for simulating IMU, GPS, etc. And then also the custom plugin for cone detections, or how would our perception systems actually see these cones in the real world, not just in simulation. And things also get very interesting when you start thinking about it, how you can use the simulation for automatic testing. In our case, we use it as part of our CI pipeline for full automatic system tests and performance analysis. So anytime somebody makes an important commit, the whole system, the whole software is put through instant simulation. We make sure that the car still drives and performs well in the simulation, and we also record some statistics of how lap times change, how the performance vary in general. And yeah, both my team and Adrian's team simulations are open source.
So another tool that is very useful for Formula Student, and I think personally for any robotics project, is you have to have some sort of centralized data storage and analysis. So instead of sending someone, oh, find the ROS bag from this time and this date that failed, and you download every ROS bag and try to figure out which one it actually is, having something like what AMZ built internally and open sourced as well, like the ROS bag bazaar, is a nice way that you can kind of communicate what a bag is about before you download it. So what the ROS bag bazaar is a data storage and visualization platform. So as you can see in the image, you can get the list of bags on the left, and any bag, it'll automatically generate and display the videos from the video streams on the card, as well as it will run the bag through the RViz and scrape all the RViz visualizations into a video as well that runs in real time. So instead of having to download a bunch of bags, figure out which one has a problem, you actually can just go look at the visualizations that are generated as well. And it also has some easy debugging plugins, like the example is the purple on the bottom is node message frequencies. So you can quickly tell if a node failed while it was running. And of course, it supports tags and filters and that sort of thing, so that you can really easily find bags that you need to analyze or take a look at, or things to run your new code on so that you can see if a bug got fixed. And with that, that takes us to our conclusion, which is in the, well, actually, no, it takes us to the video that's I would say, most indicative of how Formula Student looks, the driverless portion. Fortunately, we don't have sound, but you can imagine a nice high-pitched motor whine. So this is the 2017 AMZ car, just about to finish its mapping lap. You can see there's some RRT planning in there and some FastLab mapping. And once the lap is completed and the whole course is known, it'll switch into a faster control mode, which is the model predictive contouring control. And you can see, even in this low frame rate real redo of the video, it's very fast. And at times is really getting close to the limit of what the car is capable of in terms of grip and acceleration. If you want to see the video in a better quality, I recommend going to the AMZ Racing YouTube channel where you can find it. Cool. And on the actual conclusions, so we'll talk a bit about the things we've learned while doing the Formula Student Driverless experience. One of the main things I learned is that alumni are the key to success, or at least the key to dynasties in student competitions like this. AMZ has the benefit of many alumni who are still in the area of Zurich and are willing to talk to and mentor the students who are on the team right now, whether it's to bounce ideas off of or to just do design reviews or these sorts of things. It's very helpful to have people who have gone through what you've gone through already to answer the questions that you have. Another one is that simulation and data infrastructure makes testing time more valuable. If you show up to the test track and you haven't done some simulation tests on your code and you find out that the versions of different controllers that you have together don't work together, that was something you could have done before you got to the test track, and that wastes a lot of time when you're there. And then data infrastructure lets you, after the test day, be more efficient in utilizing the data that you've gathered. For debugging, visualizing everything is really the best way to go, in my opinion. Having worked on these complex robotic systems where just looking at the numbers and the graphs isn't going to help you as much as another system, seeing what the car and the robot think it's trying to do and what it thinks the environment looks like is probably the best way for you to build your intuition about what the system is actually doing. And another thing that we at AMZ do not follow very much, but know, is that testing and tuning will get you 90% of the way with a simple concept. So having a PID controller at minimum curvature optimization will get you to 90% of the performance, if you do it well, of a fancier model predictive control with lap time minimization and all that. And then a fun fact for everyone to know is that if your SSD gets hot, it will start losing write speed. So don't let your SSDs get hot in your robot or outside of the operating temperature ranges.
So yeah, and a couple of tidbits from me. Formula Student really taught me that teamwork and cohesion are often the biggest asset in very highly technical projects like this. And you should never assume that like teamwork is magically there if you find the right people. Teamwork is actually something you have to build and then treasure and maintain. But in my experience, it is by far the most important aspect of any team, be it students, company, or whatever. The next important thing is that I think that motivation can be built up in people and also has the capacity to fill in knowledge and time gaps in people. Oftentimes, you can find people who are not very knowledgeable or experienced, but are highly motivated, and that motivation by itself can fill in their knowledge gaps in the time. Next 2 points kind of echo Adrian, so I'm not going to spend too much time about it. But yes, echoing his thoughts completely. I think that when developing complex systems, it is best to start simple, start with simple, reliable, and easy to understand algorithms. Apart from like getting you 90% there to the concept you want, it also lets you start simple, set the infrastructure, set the glue in place to put all of your systems together and make them work as one big whole. And once you actually get to that point, it's significantly easier to get smarter and build some more complex algorithms. And yeah, I think with that brings us to the end. Thank you for listening to us for about half an hour now. And yeah, Matt, should we accept questions now?
We already in the chat. So maybe I will go over them one by one. There is a question from Roland. What are all the green parts? But I don't know what it refers to.
I think that would be MPPI slide, probably. Yeah.
Do you have the presentation on? Because I cannot see it anymore.
Not now. Green stuff. Would it be here?
In the planning section.
Do we have any way to ask the question giver this?
It said back in the path planning section. Is it the global or local?
Local.
Yeah, so the green line here is just the planned path by the car, which in this case is the middle path of the track.
Okay, so in the video, that is a visualization of the RRT that's running for path planning. So in the first year of AMZ, it was a very different system than the one we've presented here. It was a cost function based system with an RRT to plan the final path, and the path is chosen is the path that's lowest cost based on the cost function set by the cones, the velocity that the car is taking. And each of those green extra paths is a branch of the RRT that's been built. So those are the possible paths that are feasible that the algorithm found, but they're just not the best cost paths.
It is a very sexy visualization.
Mm-hmm.
Yeah, it's cool. Okay, next question is from Josh. Which version of ROS is the ROS-back Bazaar currently compatible with?
So the published version is, I believe, compatible with Kinetic. We have a melodic version. I don't know if the one that's on GitHub is updated to be with melodic yet, but it should be possible. It's definitely not compatible with ROS 2 yet, though. It's just not designed for it yet. Because the teams, at least AMZ team, does not use ROS 2 yet.
Yeah, an addition from me is it looks like something that everyone I know needs. So I will definitely check it out, and I will probably feature it in Weekly Robotics.
Yeah. I would say if you do that, we've got to put more effort in on an AMZ side to maintain it properly, like to get the versions that are used internally out.
Yeah, it looks really useful. Then we have a question from Roland. How does it pick the final path? But I don't know if it's related to the lattice planner that we've seen before.
I think we covered it, but
okay. So let's move to the next one. There's one from Joe Speed. Hi Adrian, in the Autonomous Challenge, race cars have 2 times Samsung Evo 970 Plus and VME SSDs. Might you guess that they might need heat sinks or other thermal solution? They will be used to record ROSBAC 2 for 3 times LiDAR, 6 times camera, GNSS at all.
So on our one Evo 970 Plus SSD in our car, we get 2 HESI LiDARs, 140 beam, 164 beam, and then 3 5 megapixel cameras that are cropped. So we have no problems when everything's on good heat. So I think that together those 2 could handle that level of data. In terms of the times that we had this problem was peak summer, and the way all our computer is set up is everything's in a metal box together. There's a cooling system going through the box for water cooling the CPU and the GPU separately, but there was no heatsink or any thermal components applied to the SSD. And in the summer when we were testing, this started to become a problem when the car was sitting out in the sun for anything more than 10 minutes. So I would say that assuming that this challenge is going to take place in the summer, in the sun, then yeah, I would put some heat sinks on the SSDs themselves. If it's going to take place in fall or winter, I don't think it could be even close to a problem. It's just the ambient temperature causes a lot of problems.
We have another question from Rodrigo. If you hit one cone, are you disqualified?
So there's a certain number of seconds penalty for every cone hit. So if you were to do a lap that was 20 seconds and you hit 2 cones, you would I think your final lap time would be adjusted to be about 24 or 26 seconds. I don't remember the specific time penalty per cone though. This can be very significant when you have 2 cars that are within 1 or 2 seconds of each other in terms of lap time.
Then there's an offer from Josh. I would be happy to help update to ROS2 in my spare time. I assume this is Rosbach Bazaar.
Yeah. Talk to me. I'll put drop my email in the chat, and we can chat over email or another system afterwards.
Okay, I will check if there are any more questions because there is a discussion going on there. Yeah, I think that covers all. Unless I missed anything, then just let me know in the chat. That's probably it then.
I'll stop sharing.
Cool. Thanks a lot, guys. Super interesting. Oh, maybe one more question from me. What kind of update rate would you get from the EKF for a robot like this? Or would you expect to get?
So I can speak for ANZ, and we have a slightly different system, which is that we have a real-time ECU running a Simulink model that runs an EKF as well, but only calculates the velocity of the car that can be integrated at a later stage. And that thing's running at 200 hertz real time, mostly based on the IMU frequency, basically.
That's cool.
EKF 400 hertz. Again, as Adrian said, based on the IMU frequency, which is our highest frequency sensor. But I don't think I think we actually ended up using that at 150 hertz simply because the rest of the systems couldn't handle that much data throughput.
Cool. Okay, so let's hand it over to Josh now.
Awesome. Thank you very much, guys. That was really interesting, and I'm sure I'll have a few follow-ups for you, too. So my name is Josh Whitley. I'm the software architect with the Autoware Foundation, and let me go ahead and share my screen. Just a moment. All right. So I'm going to be kind of giving an overview of the Autoware Foundation and the software that we provide for autonomous vehicles. So as I said, I'm Josh Whitley. In addition to being the system architect for the Autoware Foundation, I also have my own consulting company called Whitley Software Services. And that picture is on the right is of me and my wife, Kathy. So the first question you might have, if you haven't heard of us before, is what is the Autoware Foundation? So the foundation was started based on a piece of software called Autoware AI, which was created in 2015 by Shinpei Kato at Nagoya University. So Autoware AI is currently supported by the largest autonomous driving open source community. There's a little over 4,000 stars on GitHub now, and now we're at a little over 2,200 accounts on Slack, specifically targeted to the Autoware Foundation, which includes Autoware AI. There's widespread international adoption. Autoware AI is used by more than 100 companies and runs on more than 30 types of vehicles in 20 different countries. And there are courses using Autoware offered in 5 countries. Automotive OEMs are also using Autoware for mobility as a service software development. And it's been qualified to run on driverless vehicles in public roads in Japan since 2017. One of the founding companies of Autoware AI, Tier 4, currently runs Autoware.ai on Robotaxi service in downtown Tokyo, Japan. And now we're developing Autoware to move beyond Autoware.ai to take it to the next level. We'll talk a little bit more about that later. So if you have any general questions about the foundation, Autoware.org is the starting point for all of our products and membership. So just a little bit about the foundational structure. The members are kind of the base of our foundation. So we have 3 different levels of membership, and most of the members occupy the task forces and work groups. But those are also populated by members of the Autoware community, which by extension includes the ROS community. So our task forces and work groups are completely open to the public, and they're the groups that really produce all of the tangible work that comes out of the foundation. We also have a technical steering committee, and we've recently added a strategic planning committee as well. And those 2 high-level committees are populated by just member organizations, because each of them has a voting seat on those 2 organizations, and that kind of decides the high-level goals and direction of the foundation. So the technical steering committee produces our technical projects and also decides the operational design domains, or ODDs, that we're going to target with our software. And then the technical steering committee and strategic planning committee are overseen by our board of directors. So here's just a list of many of the current organizations that are part of the Autoware Foundation. You'll see some big hardware vending names in there, like ARM and Velodyne, AD-Link, Street Drone, etc., NXP. So they are all members of the foundation, and they help us decide where we're going to go next with our software products. So the current projects that we're working on are Autoware AI, Autoware.Auto, and Autoware.IO. And we'll just briefly go through a couple of those and then focus a little bit more on Autoware.Auto near the end. So Autoware.IO is really meant to be like a connection platform for ways to connect hardware vendors and sensor vendors and so on with Autoware AI and Autoware.Auto. So things that they would include in Autoware.IO would include like heterogeneous hardware reference platforms. So you can do CPU-based or GPU-based compute, and you can run Autoware.Auto or Autoware.ai on these platforms. And they also provide things like BSPs or compute or API layers that allow you to run these ROS-based platforms on embedded systems. This also includes plugins and software that's developed to allow closed source pieces of software to integrate with Autoware AI and Autoware.Auto, which are completely open source. So if you want more information about the Autoware.io project, you can go to Autoware.io. There's also a hardware reference design that was produced by one of our members called AutoCore, and a BSP to allow you to run Autoware AI on that reference design. And then there's full documentation for that PCU, which was developed for Autoware AI. So Autoware.ai is the ROS1 version of an autonomous driving stack. So it was originally intended to be a full self-driving stack, SAE levels 3 or 4. It's meant to support many vehicle platforms. It contains launch files, configuration files, pre-trained example neural networks, and example maps that you can use in a simulation environment or just with RViz. And the primary website for that is at Autoware.ai. And then you can see all of the available code on github.com/AutowareAI/Autoware.ai. And the documentation is on a wiki that is attached to that website. So the primary Autoware AI GitHub account is actually a kind of a core GitHub repository. And this links to all of the sub-repositories that are part of Autoware AI through a repost file. So you use a tool called VCS to populate a copy of all of these GitHub repos into subfolders, and then you build the project as a whole to include all of our perception modules, planning, all of our messages, simulation utilities, visualization, etc. And then the primary documentation, as I mentioned, is on the wiki, which is attached to this, this GitHub site, which includes information on installation from source or through Docker, a couple of demos, and then how to get support and how to contribute to Autoware AI. So as I mentioned before, it was started in 2015 at Carnegie Mellon University by Shinpei Kato, now handled by Nagoya University. And many of the features were initially developed by the students at Nagoya University, mostly as like postdoctoral research. And the first official release was in August of 2015. So Shinpei Kato then formed a company based around Autoware AI, which was called Tier 4. And it was formed in December 2015. And they provided most of the development of Autoware AI until around mid-2018. We also had some back and forth as far as where we're hosting it. It was originally on GitHub, then it was moved to GitLab, and now it's back on GitHub again. So the GitLab version will redirect to GitHub if you happen to go there. But regarding the current status of Autoware AI, one of the best examples is a fork of Autoware AI called the Autonomous Stuff Open Autonomy Pilot. It's very slightly modified from the official release of Autoware AI, but it essentially has all of the same APIs and just has extensions. So if you'd like to go to Autonomous Stuff's website, you can check out more information about their autonomy pilot. And this is just an example video of Autoware AI running on a test course at Autonomous Stuff. You can see the hexagon logo. Autonomous Stuff is owned by that parent company. So the vehicle is detecting the traffic light in front of it and the traffic light state. You can also see in that video that it was fusing the LiDAR data with camera data. And then as soon as the light changes color, then it automatically knows to proceed through the intersection. So some of the drawbacks associated with Autoware AI is that since it grew organically out of student projects, it was not really designed initially for functional safety. And it's the project itself started fairly early in the autonomous vehicle revolution. So it's really good for research and development and testing. And also, if you haven't moved from ROS 1 to ROS 2 yet, it's the great platform to kind of get an idea of what's possible in ROS 2, or excuse me, ROS 1. But it's really recommended that if you're looking for functionally safe applications, that you want to move to ROS 2 because of a lot of the advantages that are inherent in the ROS 2 system. So the last major version of Autoware.ai is actually being released this month in March of 2021. And that will include the last features that are being added to Autoware AI. So from this point forward until December 2022, the product will be in maintenance-only mode, which means we'll accept only bug fixes and small non-breaking changes. And then as of December 2022, Autoware.ai will go end of life. So that brings us to Autoware.Auto, which is really the future of where the Autoware Foundation is going. So the Autoware.Auto project is based on ROS 2 and the underlying message transfer system DDS. And we primarily focus on the Cyclone DDS implementation because we're very familiar with the organization that develops Cyclone DDS, and we're very impressed by their performance metrics compared to other DDS vendors. So ROS 2 is, or excuse me, Autoware.Auto is a full open source autonomous vehicle software stack. And the way we develop Autoware.Auto is by targeting specific operational design domains. The Autoware.Auto stack is intended to provide a modular reference design with very clearly defined APIs between each of the major modules, so that if you want to implement your own replacement for any of the functions within Autoware.Auto, you can very easily do that by just looking at the messages that are being passed back and forth between that module, and those messages should stay fairly static across releases of Autoware.Auto. You can check out the usage and API documentation, which is auto-generated from the code and also from a huge number of documents that we've produced for usage and for building and for development practices at the link that's in this slide. And we'll look at that interactively in a little bit. So some of the main advantages of Autoware.Auto over Autoware AI and many of the other open source self-driving stacks is that from the ground up, Autoware.Auto was developed with safety, code quality, static memory allocation, and documentation and modularity all in mind. And we keep all of that in mind when we look at every merge request that we receive to Autoware.Auto. So you can check out the website at Autoware.Auto, or you can go to the GitLab repository to look at the actual code. Real quickly, a little bit of history about Autoware.Auto. It started in August 2018, and most of the initial framework was developed by Apex.ai in partnership with Tier 4. Apex was a previous member of the Autoware Foundation, and they are continuously doing ongoing development, even though they are no longer a member of the foundation. The active development of the primary ODD-based development is managed by the Autoware Software Working Group, which I'm the chair of. And the meetings for the Autoware Software Working Group are open to the public. So if you want to check out that link to our shared calendar, you can see each of the meetings that we have. Because we are an international organization, we rotate through 3 time slots, a different one every week. And hopefully we try to hit all of the major time zones with each of those time slots. So if you can't make one because of the time, just look to the next week and hopefully you can make that one. And then the first official release of Autoware.Auto was just this last month in February of 2021, which was our 1.0.0 release. And I'll talk a little bit more about that in a few slides. So our 1.0.0 release targeted ROS Dashing and ROS Foxy, but all of our development going from this point forward will be only on Foxy and on Rolling and Galactic and all of the upcoming releases. So we've essentially deprecated dashing support as of the 1.0.0 release. We offer 2 ways to work with Autoware.Auto. You can just download the code if you want to and install it on an Ubuntu 1804 or 2004 machine if you're using the 1.0 release, and just build it as a from source environment. But you do have to install all of the dependencies and make sure that you have the capabilities you need inside your host environment. But we also offer a Docker-based environment, which is based on a tool called ADE. And ADE allows you to spin up multiple Docker environments and multiple Docker containers and volumes all at the same time, so that you have access to an environment that has all of the dependencies for Autoware.Auto, and also environments like in an IDE where you can do your code development, and a simulator where you can run real-time simulation and feedback data. And all of that runs within the Docker environment, both of which support natively x86 64 environments and ARM 64 environments. So you can also run this code on like NVIDIA Jetsons or even a Raspberry Pi. So the current 1.0 release supports the functions that include, we have a point gray or FLIR camera driver built in. But keep in mind that all of these are using standard ROS messages like sensor messages image. So it will support almost any hardware outside, but these are the built-in drivers that we have available in the stack. We support Xsense GPS and IMUs through a built-in driver, and we have our own version of the Velodyne driver, which is separate from the community-maintained version. And the reason we did that is because we wanted to create a version of the Velodyne driver that has all static memory allocation and is flexible and easily modifiable to support new versions or new sensors. So we just developed our own, and we are planning on releasing that separately from Autoware.Auto to hopefully live alongside the community-maintained version. So the current version also supports localization through an NDT matching-based algorithm on the LiDAR data. It supports ground filtering using a ray classifier. It supports object detection using a voxel grid implementation and also Euclidean clustering. We support vehicle interfaces, currently through Linux SocketCAN or simulation-specific interfaces, but also we'll be adding vehicle interfaces for other simulators in the near future, and New Eagle drive-by-wire systems, and possibly autonomous stuff PackMod drive-by-wire systems. And it's also fairly easy to add a new vehicle to Autoware.Auto, and we'll have instructions on how to add a new vehicle up very soon. We're working on that right now. And then most of our motion control is done through either a pure pursuit algorithm or a model predictive control algorithm. So the first operational design domain that we targeted with the 1.0.0 release was autonomous valet parking. And currently, the ODDs that we're targeting, now that we're finished with the autonomous valet parking, are cargo delivery within an industrial environment and racing, which covers the Indy Autonomous Challenge and the F1/10 organization, which targets like 1/10 scale RC vehicles. So as part of the 1.0.0 release, the architecture that we designed for autonomous valet parking, this is like a high-level overview of the nodes that are running within the primary launch file for AVP. So we intended it to have at least 2 LiDARs, a front and a rear. We then transform the data from each of those LiDARs into a common frame of reference. Then we do point cloud fusion to fuse together the point clouds from each of those LiDARs. And then from there, the fused point cloud either goes into our perception stack or our localization stack. So for localization, we downsample the point cloud, and then we have an NDT localizer, which matches the scan references against a known point cloud that was taken from the environment previously. For perception, we then run the fused point cloud through our ray ground filter, and then through a Euclidean cluster detector, which will create bounding boxes associated with each of the detected objects. And then we have a collision estimator, which is part of the planning architecture. So the planning architecture is based on a Lanelet 2 format map, which is a high definition semantic map definition, which provides things like lane boundaries, traffic rules, intersection information, and those sorts of things. And we load that into the environment and then make it available for all of the planning modules within the planning architecture. So when you want to navigate from one place to another within the Lanelet 2 map, you give it a pose estimate of where the vehicle is, which is normally given by the NDT localizer. And then you give it a goal pose of where you want to travel, and you can do that through either RViz or a web interface, or just publishing it directly on the terminal. Then the global planner will use the HD map to dynamically plan a route through the road network, and then it will pass that global route to our behavior planner, which is what looks at the current ego vehicle position and estimates the position on the planned route. So the behavior planner will then call a set of sub-planners, which plan different maneuvers based on the type of HD map primitives that the route is planned through. So if we're planning along lanes, we use the lane planner to essentially generate like an artificial center line, and then attempt to follow that center line with the controller. Or if we know that we're going to be moving into or out of a parking spot, we use the parking planner to plan a complex multi-point maneuver to move into or out of that desired parking spot. And the behavior planner conglomerates those into a complete route, which is then sent as a trajectory to our MPC controller or our peer pursuit controller. And then the controller turns that into to steering and pedal commands, which are sent to the vehicle interface, which interacts either with the simulator or the vehicle drive-by-wire system. So that's the very high-level overview of the primary architecture that's being used for that was used for the autonomous valet parking. But we also have a lot of extensions that are being done to that as part of our cargo ODD and racing use cases. So this is just the starting point. So regarding the cargo delivery ODD, I just kind of wanted to give you guys an idea of what our future development looks like. So currently we are in the first milestone of the cargo delivery operational design domain, which is kind of our background and prep, which means extending the architecture to be able to handle many additional ODDs and replacing a lot of the messages from the Autonomous Valley Parking demonstration with much more flexible message APIs, so that we can do things like add additional inputs for our perception architecture and use different localization algorithms and not depend specifically on LiDAR-based localization and those sorts of things. So we have about a 6-week milestone development period, and the first milestone, we're doing just those retrofits to include the new architecture features, and also to kind of clean up some of the things we wanted to be able to do during the AVP development cycle but didn't have time to. So the rest of our development cycle is going to include targeting outdoor driving and specific features related to that. We'll then have a 1-week hackathon that will go on between the first milestone, or the second and third milestones. And then we have indoor driving. So one of our use cases for the cargo delivery ODD is being able to move in and out of buildings in an industrial complex. So we have to be able to handle the light transitions and the sensor limitations associated with very close detections and those sorts of things. So the indoor driving will be the focus of an entire milestone. Then following the indoor driving, we'll have a 2-week integration period where we go to our demo location and we'll work physically on the vehicle during that time, making sure that the software is running just as well as it was in simulation, that we're communicating with the vehicle drive-by-wire system as well as we were in simulation, and that everything is ready for our actual demonstration. These dates are somewhat subject to change, but right now we're targeting sometime around July 16th for our demonstration of the cargo delivery ODD. And during that time, we will be doing, we're currently working with a member organization of the foundation to potentially do this as a demonstration at an airport with a cargo delivery vehicle that will go to the airplane. The baggage handlers will load it up with cargo in platforms that are following the lead vehicle. And then it will autonomously drive from the airplane across the tarmac into the luggage room and dock up against a luggage carousel where it will be unloaded by people and then autonomously drive back to the next plane. So that's the hope for our demonstration and what we're targeting. And then we always have a milestone after our primary development cycle that includes cleanup and technical debt reduction, just to make sure that our documentation fully reflects what we actually have in the code base, and that anything we needed to kind of rush or want to follow up with actually gets finished during the development cycle. We also keep a long-term backlog of issues that are not directly related to the current ODD that we're targeting. So if you're interested in doing some development on the Autoware.Auto project, but you don't have time to join the software workgroup calls and look at exactly what we're working on for this milestone, then you can always go to the long-term backlog and look at issues that don't have any specific target date associated with them, and we would just like to complete at some point in time. So final few slides here. You can follow along with us on GitLab for the list of issues that are associated with Autoware.Auto. If you have never contributed to open source before, there's a link here to a GitHub repo that gives you a step-by-step tutorial on how to clone down a repository to your host machine, how to make changes to it, how to make a pull request to the original repository, and so on. All of the main steps you need to be able to understand for contributing to an open source project. As I mentioned earlier, we have a Slack site dedicated to the Autoware Foundation and to Autoware Foundation projects. So if you want an invite, just go to this address and you'll automatically be able to join our Autoware Slack. We have a whole category dedicated to Autoware on ROS Discourse. And then if you're interested in joining the foundation, either as an individual member or as an organization, you can send an email to auto@autoware.org to get information about joining the foundation. And then if you want support for any of our specific projects, the documentation, I mentioned the links there earlier, And then Ross Answers is really the primary location where we ask people to go to get started with asking a question about Autoware. So this allows us to have the community's help in answering these support questions. And then if any of those support questions get turned into bugs or feature requests, they get added to the list of issues on the Autoware.Auto repository. And that is the end of the official presentation. I briefly wanted to give like a couple minute demo of this actually running in simulation. So if do you think it's all right if we have time for that, Matt?
That you need.
I'm sorry?
We have all the time that you need. Go on.
Okay. So I've got a couple of terminal windows running here. I'm running on an Ubuntu. I'm actually running on an Ubuntu 2010 machine, which is not one of the supported environments. So I'm running everything inside our ADE Docker-based environment. So you just have to run one single command to start up the ADE environment with all of the Docker containers for Autoware.Auto. And then in the first Docker container, I'm running the LGSVL simulator, which is just running a single command again. And that is running down here on a different desktop. So I will get the simulation started. You do that from a web interface. And I've already configured a vehicle and a map to run the simulation, which I've set up as the autonomous stuff with Lexus simulation. So once I start running that, you'll see the simulation get started down here, and I can drive that around with keyboard controls. But then what we really want to be able to do is connect that simulation to the Autoware.Auto software. So in another window, I've gone into ADE just by running ADE enter, and then I've sourced our installed version pre-built binaries of Autoware.Auto. And then I'm going to run a launch file that we generated for our autonomous valet parking demonstration. And this is the simulation version of it. We also have a real vehicle version of it that connects to the drive-by-wire system instead. So once this starts running, I'll get an RViz window. I'm going to take that RViz window down with me to my other screen. And then you can see down here, we have the high-definition map, which is a Lanelet 2 format. And then we have a location of the vehicle. But right now, the localizer doesn't understand where the vehicle is in the map because we're not using any GPS information. So we have to give it a pose estimate to just kind of show it where to start. And then as soon as I give that pose estimate, you can see it snaps to the location where it's at in the real map. And you can see all of the obstacles in the LiDAR point cloud around the vehicle. And as I drive, the point cloud will update as well as my position on the map. So I'm going to kind of drive to the starting point where we have a predefined pickup and drop-off zone for where people are supposed to be getting picked up and dropped off by the autonomous valet parking demo, which is in front of the autonomous stuff building in Silicon Valley. I'm going to make a turn here. You can see there's a little bit of delay in the detection of obstacles in the LiDAR point cloud, and that has mostly to do with visualization and very little to do with the actual detections. But I'm going to do this essentially the same way that we did it during our live demonstration, and that's through another web interface. So I'll load up the web interface. Also, I can just hit return to drop-off area, and it will plan a route out of the parking spot and then back to the drop-off point.
Josh, sorry, but I think actually you lost internet a moment ago, and I don't think it was recorded.
Okay. So are you able to see the vehicle driving on my screen right now? I'm wondering if maybe me having it off on a different screen or monitor caused a problem.
or maybe the servers went down for a bit.
Okay.
Yeah.
Are you able to see the
It's
simulation on the
working.
Argus window for me right now?
Yes.
Okay.
Yes, it's.
So yeah, that was just a quick demonstration of the features that we added for the autonomous valet parking, and that is all I have for the run through.
Thanks a lot. It was really, really interesting. We have lots of questions from Adrian and Ignat. So I'm wondering if it's useful for you guys to unmute yourself and ask the questions yourself. Maybe.
Roll through my list of questions and we'll go over the ones that we asked. First question I had was, does the Autoware project have all the data infrastructure systems also being built together with the from what I've seen, it's a lot of on-car projects. But what I've seen from the really big autonomous driving companies is that they have an even larger than their car fleet data and simulation infrastructure that really accelerates their development process.
Sure. So right now, the simulation is like per machine, so you have to run the simulation locally. But LG develops the LG SVL simulator. They're about to release a new version of the simulator that allows you to choose scenarios and environments and have them automatically run on a cluster that's on like the Amazon Web Services cloud. So you can run a batch of simulations and have them all run dynamically without touching anything. And then the next step to that is we're also working to have a full scenario-based simulation pipeline. So each one of these operational design domains that we target is defined by an ODD workgroup. And in addition to defining the ODD, they also create a huge list of use cases and then turn those into a machine-readable format, which can be loaded into a scenario generator and simulation pipeline.
Oh, okay.
So every time we finish an operational design domain, we use that as our completion list, right? So we will make sure that we can complete all of these use cases and that we actually implemented all the software and it works the way we expect it to.
Cool.
Yeah.
Let's see. Next question. Me again. What does the certification landscape look for something like this? I'm from Mountain View, and I see these autonomous cars. Like, new companies are popping up all the time, and you just see a Prius with some tube steel on top and a LiDAR, and you wonder, like, is it driving autonomously? What's the software looking like? What does that look like for Autoware?
So because the Autoware.Auto project is designed to be flexible and designed to be a reference implementation, we are not specifically targeting certification for the Autoware.Auto project. However, many of the member companies of the foundation want to be able to certify it. So because of that, we try to stick to things like MISRA compliance and static memory allocation, and the sorts of things that you need in order to get certified for like ISO 26262 or SAE certification. So we make it as easy as possible for our members to be able to do that while retaining the flexibility of an open source project that is being used in lots of different use cases. As an example, one of our member companies, Autoware or Apex AI, they develop a hardened, certified ROS2 fork, and it's API compatible with ROS2. And they also develop a certifiable version of Autoware.Auto. So you could run everything from the kernel level up to be an already ISO 26262 certified stack that has Autoware.Auto as its base.
I see. Cool.
Yeah.
Next question, also me. How has the ROS2 experience been? I always look once a year on what the status of everything is. And I guess being in research, I'm not pushing for real-time stuff. I'm pushing for things that are stable enough that I won't run into problems. But I'd love to hear a first-hand experience for how it's been with ROS2 so far.
So dashing and before were a little bit rocky. There were a lot of nodes that just had and features that just hadn't been ported to ROS2 yet. The community is fairly quickly catching up though, and Foxy definitely has, I'd say, like 90 to 98% of the features that were described in the design documents for what ROS2 is supposed to be. So it's much more smooth than you would expect, and just the fact that it has DDS as its underpinnings makes it so much easier from like a multi-node, multi-ECU environment. So, for example, like the biggest thing to me is if you're running nodes on one machine on a network and you're running nodes on another machine on a network, there's none of this crazy stuff from ROS1 where you have to set like ROS URIs and make sure that the ports line up and all of that. There's no ROS core. So the ROS core runs as a service on every machine, and they auto-discover each other and can connect across nodes on the network with no configuration. It's awesome.
ROS has made it to the 2005 networking stack, I guess.
Yeah, but you get all the extra stuff of DDS too, like quality of service and security, and like all of that's just built in. It's really nice.
Yeah. Guess the next question was Ignat, but it was also a little answered in the chat. Do you want to ask it, or should I ask it, Ignat?
So I can go ahead. Yeah, my question was, do you find Arvis in ROS2 sufficient for anything?
Yeah, Arvis 2 definitely in Foxy has made huge improvements. One of the things that was missing prior to Foxy was the ability to subscribe to, in ROS1 you call them latched topics, but in ROS2 they're topics with transport local QoS. And that has been added in Foxy. So I've been pretty happy with it. There are some things that I would like to see added, and some things that people are working on in a completely new framework for Arvis 2 that I think will be released with ROS2 Galactic.
Okay. The next question was me again, but I think you kind of answered it, which is the question about whether HD maps are supported by Autoware and how they're managed. I do have one question on top of that, which is is it that every company that's going to use an Autoware system in their area has to go drive an Autoware car through it and do the pre-mapping that way, or is separate, or is it a more separate project?
Yeah, so there are kind of two answers to that question. One that comes out of that is an HD map required? And the answer to that is no right now. You don't have to have an HD map to be able to use Autoware. But you do gain a lot of additional features by using one. So if you don't have an HD map, the primary requirement is you have a LiDAR-based point cloud of the area you want to be able to run. And you can go record that by just putting a Velodyne on a stick and go walk around wherever you want to go to create an HD map with a laptop. And it doesn't specifically have to be from Autoware itself in order to use it. Let's see. Oh, okay. Thanks for coming, Ignat. Appreciate it. And then regarding the HD map itself, you gain the ability to do dynamic planning. So Autoware.Auto does not have the ability to do planning without an HD map right now, but we are adding that as part of the feature set for the Indy Autonomous Challenge and the F1 10th Racing. So it will use SLAM auto-generated maps as the routing infrastructure and be able to do that for those two use cases.
Awesome. And then I think this was the last of my questions, which is how is ROSBAC 2? But I was reading Joe's links about some latest improvements, and they sound pretty great. So I am a bit, because I found the choice of like using a database as a file format very interesting, especially given that a lot of ROS messages are not indexable, or they're just binary blobs that are kind of opaque. But I guess the goal there was to add SQL support, right? So that to make a more interesting ROS bag API.
Yeah, and it allows you to do a lot of fast indexing that you can't do, without that well-defined structure. And also with regard to the ROS2 messages, the message format is only slightly different. It's extended a little bit for ROS2, but every message you define, whether it's an action or a service or a .msg file, those get turned into an intermediate language, which is the IDL language, and then they get compiled to a DDS-specific implementation for the ROS2 transport. So the IDL layer is really what gets stored in the ROS bag, and so the definition for the data structures in that are a lot more well-defined than the ROS message structure.
Okay, good.
So let's see.
We have some more questions. So Roland asks, said, I'm sold. Does this also work on a real car right now? And what car should I buy to try it on?
Yeah, absolutely. So we did a demonstration in San Jose, California in October of last year. And it was working on a real vehicle, which was using a Lexus RX 450H, which is a hybrid. And then it was outfitted with a PackMod drive-by-wire system from Autonomous Stuff. And actually, if you go to our documentation and go under, actually the homepage for the documentation has a video of the autonomous valet parking demonstration on the real car. But as I said, right now it has two vehicle interfaces, one to the simulator and one to the Autonomous Stuff speed and steering control software. But we are just about to merge a merge request to be able to support any drive-by-wire system that's created from New Eagle. And we're in the process of creating one directly to talk to the PackMod without the speed and steering control.
Wow, that's cool. I can't wait to see this on some cars.
Yeah, our next demonstration will probably be in conjunction with like a small tug vehicle that will be pulling cargo on the tarmac at the Seattle, Washington, Tacoma airport.
That's cool. That's a good application for autonomous cars as well, I imagine. And Joe had a question as well. Who are our US East friends that gave tool for porting Volkswagen HD map datasets to Autoware, or was it Volvo? Maybe if you look at the chat, you will have more context.
This was from Joseph.
Yeah.
Let's do devised, use equals Adam Dabrowski from Robotech AI. Cloud version. Sorry, I'm not seeing that question there.
It's just after Ignat left. It's literally
okay.
7th question from the bottom.
Okay. Who are our US East friends that gave tool for porting VW's HD map dataset to Autoware? I actually am not sure. I'm not familiar. He says never mind. CTAC. The two guys. Yeah, I'm actually not sure of that. I hadn't heard about that, porting the VW's HD map to Autoware. I'll have to look into that.
Okay. Well, that's some homework then, I guess.
Yeah, absolutely.
Okay, cool. So assuming there are no other questions, you remember. So maybe we'll take it over. We will end the broadcast now, and we will have this group chat now, and you guys will get to the you will find the supplier. All right. So thanks a lot, Josh. I will end the recording now, and talk to you in a few seconds.